In Unit B, we talked about simple interest, and we mentioned compound interest, where you pay interest on the interest. In Unit C, we're going to investigate that and look at techniques for dealing with compound interest. Suppose Marty borrows $1,000 at 10% per year, and he plans to pay it back in 3 years. And his mother, if that's who it is, said, "I'll only use simple interest." He's going, "Thanks, Mom." And his mother goes through the calculation and discovers that at the end of it, the amount that he owes is $1,300, and he looks a little annoyed because it's $300 interest. God, borrow it from a parent and have to pay $300 interest? Unheard of. Let's, for review, look at how that simple interest calculation would work. Remember that the interest is the principal times the rate times the time, or PRT. Putting those numbers in, $1,000 at 10% interest for 3 years, changing the percent to a decimal, we would see, as your quick in-head math will tell you, that's $300. Suppose we did it year by year and looked at the original principal and see what happens. So at the end of the first year, the interest would be $100. At the end of the second year, $100. And at the end of the third year, $100. If we totaled all of this, we would get, after 3 years, there would be $300, or 3 times the 100 for the end of each year that you would get. This is how you could think of it with simple interest. Now let's look, though, and see how we would think about the same thing if we used compound interest. And we have to talk about how many times it's compounded. In other words, if you're going to charge interest on the interest, how many times do you add that interest in when you're doing the calculations? So let's assume we're doing it with the same 10% interest, but it's compounded. In other words, you add in the interest at the end of each year. Let's do that and then calculate the same loan. At the end of the first year, we would have $100 in interest. Then we would add the interest to the principal to get the new principal for the second year. To start the second year now, we wouldn't calculate the interest on the original $1,000. We would calculate it on the $1,000 plus the $100 interest that accrued at the end of the first year. So our principal for the second year would be $1,100. Then 10% of that is $110. At the end of the second year, for that year, we would have a $110 interest due. Then, at the end of the second year, we would have to add in that $110 to then calculate the interest for the third year. Adding the principal at the end of that we started, then the interest at the end of the second year to get the principal we're going to begin with for the third year. That's $1,210. All right, now we take the 10% interest on $1,210, which includes the $1,000, and the interest that we've done previously, that's $121. At the end of the third year, what do we owe? We owe $1,331, so the principal is $1,000, but now the interest payments, because we've compounded it, we've added in interest on the interest for the previous 2 years, it's $331. You remember that the original interest that we figured using simple interest was only $300. By paying interest on the interest, we had to kick in another $31. This is called compound interest, where as you accumulate the loan or you have a savings plan that pays you money, having compound interest is good when it's working for you, and of course, bad when it's working against you if it's money you owe. Let's take a look at the definition. The compound interest is interest that's calculated based on the principal, of course, and the prior earned interest. Let's start to develop how we deal with compound interest with the formula, or one of the formulas, for the final balance that we dealt with in Unit B. The final balance is the principal times the quantity, 1 plus the rate times the time, the interest rate times the time. Let's now plug in something for this to see how it's going to work. Let's take, for example, a fairly simple case. Let's take $1,000 compounded at 10%, with a 10% APR compounded yearly. Let's follow it along. So here, what's the balance at the end of the first year? The balance is going to be, if we work this out, the $1,000 principal plus 1,000 times the 10% times 1 year. Then we can factor the 1,000 out and then combine the terms in the brackets. 1 plus 0.10 times 1 is 1.1. At the end of the first year, we will have a balance of 1,000 times 1.1. That's at the end of the first year. Let's take that as the principal for the second year before we could actually work this out now and get $1,100. But we're not going to. I'm going to leave it in this form. The balance from the end of the first year becomes the principal for the beginning of the second year. Now, at the end of year 2, what do we have? The 1,000 times the initial 1.10, those first two quantities is the principal from the end of the first year. Then we're running it to the end of the second year. What we have now is the 1,000 original money, the 1,000 times the quantity 1.1 from the end of the first year. Now at the end of the second year, because we add in that same factor, we have 1,000 times 1.1 times another 1.1, or 1.10 squared. At the end of the second year, the balance is 1,000 times the quantity, 1.1 squared. But then what? The balance for the end of the second year becomes the principal for the third year. Here's year 3. There's what I have, the 1,000 times the 1.1 squared is the principal for the end of the second year. To find the end of the third year, I multiply it by the quantity 1 plus the rate, which is 0.10, 10%, times the time, 1 year. We're compounding it at the end of each year. If I work this out again, 1 plus 0.10 is 1.10, and look what I have. I have it's 1,000 times the quantity, 1.10 cubed at the end of the third year. You see, what happens is that factor, the 1 plus RT factor, gets put into an exponent depending on how many times it's compounded. Let's see if we can work that out. Again, just to review, we have, at the end of the first year, we have 1,000 times the quantity, 1.1. Then we have that quantity times another 1.1 by the end of the second year. Then those three factors are multiplied by another 1.1 for the end of year 3. Now we can do the calculation. I have 1,000 times 1.10 cubed. When I work that out, that turns out to be $1,331, the $331 being the total accumulated interest. Let's see how this works algebraically. The formula we can derive for compound interest is this. The final balance is the principal times the quantity 1 plus the rate times the time, the whole business to the nth power, where n is how many times you compound it. We have the final balance is equal to the original principal times the APR, the yearly rate, times the time length of each compounding in years. So if you compound once a year, the time is 1. If you compound half a year, the time is 1/2. And then the n, the thing you take to the power, is the number of times that you compound. The best way to see how this formula works is to try it with an example. Marty borrows $10,000 at 9% compounded yearly, once a year for 5 years. The principal is $10,000. The APR is 9%, which is 0.09 expressed as a decimal. And t is equal to 1 because we have yearly interest, and then we compound once a year. But then, since we're doing it, we're compounding it once a year for 5 years, our n factor has to equal 5. We need to take that quantity to the 5th power because we're doing it for 5 years, compounding it once a year. There's the formula we start with, and you notice that I have a calculator sitting there. And I have that there for a very specific reason. If you look at the formula, we have the quantity 1 plus RT raised to the nth power. So that's going to be a number like 1.06 raised to the nth power. The question is, how can you do this on your calculator? An easy way is this. Follow me. Many of you might have a scientific calculator, something that is a little bit more complicated than just what we call the standard 4-banger calculator with plus, minus, multiply, and divide. This has a bunch of other functions on it, and if I zoom in on this, I see that one of the functions here goes x to the y. That means you can take a quantity, x, 1.06, and raise it to a power y to the 5th power. If you have a powerful calculator, it's possible to do this, or there are other ways of doing it. Let's play around with calculators and look at ways that we might handle a problem like this. One of these is to hope that the n, the number I give you that has the power that you have to raise that quantity to, isn't too big. For example, if I said compounded 5 years, it would mean you might have to multiply 1.06 times itself 5 times. That's not an awfully hard thing to do. But suppose you wanted to do it with a scientific calculator. Let me show you how. I'm going to pop a couple of things up on the screen just to play with. To show you how such a calculation might work, let me pop up a calculator, and let me pop up something that will magnify so you can see what I'm doing. I'm going to start by entering 1.06 into the calculator. If I go up here, you can see it. Then I'm going to go over here to the X up arrow Y. That's the X to the Y power button, and I'm going to press that. It's registered X. Now I go back and enter the power. For example, suppose I enter a 6. Then I click on the 6. Notice it registers 6 up here, that I've put in something to the 6th power. Now when I go down here and hit the equal, it shows me what 1.06 to the 6th power is. I was able to do that. Therefore, if you have a scientific calculator, you can do these problems a little bit more easily. If you don't have a scientific calculator, all you have to do is enter 1.06 times 1.06 times 1.06. Do that 6 times. It's a little bit more annoying, and the scientific calculator will help you, but it's not 100% necessary. Given that, let's go on and work this problem. We have a principal of $10,000. We have 9% interest compounded yearly at the end of each year for 5 years. You see that's to the 5th power there. Then I have 1.09 combining the 1 plus the 0.09 times 1, and I have to take that to the 5th power. And I did it actually using this calculator that came with the Windows operating system, the one I just showed you. Then when I multiply 1.09 times 1.09 times 1.09 times 1.09 times 1.09, that's 1.09 to the 5th power, I get 1.54. When I multiply that, I find that my final balance, including the interest, compounded once a year for 5 years, is going to give me $15,400, more or less, given some round off. Suppose I take the same example with simple interest. What I'm going to do, there's the $10,000 principal, 9% interest for 5 years. If I do that, I find I have 1.45, which gives me $14,500 compounded as simple interest. To let me remind you, if we did compound interest compounded yearly, the final balance is $15,400. That's a $900 difference. It's reasonably considerable. Compound interest is much more powerful than plain old simple interest. Let's try another one. Let's try now that Marty borrows the $10,000 at 9%, but now instead of compounding it yearly, in other words, adding the accrued interest in at the end of each year, Marty is working with some kind of an agency that compounds the interest monthly. Let's see how that's a little bit different. There's our basic formula for the balance. The principal is $10,000. The rate is just the same, 0.099%. But now the time that we have is 1 month. And remember, since it's 9% APR, annual, we need our time scale. Since the rate is given in terms of years, the time also has to be given in terms of years, and 1 month is 1/12 of a year. Then N is the number of times that the interest is compounded. Since it's compounded monthly, it's compounded 12 times a year, and the loan is for 5 years. So in this case, N equals 60. I'll bet you're already thinking about, I don't have one of those scientific calculators. Well, let's plug the numbers in, and let me assure you that I'm doing this as an example, and when you do this, the numbers will be a little bit more tractable, so if you don't have a scientific calculator, you won't be sitting there for a million years. But we'll assume I do and I've plugged it in. Plugging numbers in, the final balance is the initial principal times 1 plus 0.09 times the time now, which is 1/12 of a year. And if we're compounding once a month, there are 12 months in a year for 5 years, the number of times it gets compounded is 60. So I raise that to the 60th power. 1/12 is 0.083. I could change that to a decimal. And when I do that multiplication, I get the number in the brackets is 1.0075 that I raised to the 60th power with my calculator. 1.0075 to the 60th power turns out to be 1.57. And my final balance is approximately $15,700. And there is a lot of round-off error here. I say approximately because I've taken the 1.0075 to the 60th power and rounded it down to the nearest 2 decimal places. I could have carried it out further if I wanted a more exact answer to this. For example, so now I can do this using a calculator. The first thing I do is put in the 1.0075 into the calculator. Then I would hit the X to the Y button, as I showed you before. Then I would type in the 60, the power I raise it to. Then I would hit the equal key, and finally I would read the answer. Notice that that is to a lot of decimal places, and I rounded that off to the nearest 2 decimal places, 1.57, and there's what I finally got. Often you'll see this, annual percentage yield, 5.01 on an ad or something, and when you see APY, what they do is calculate the interest as for compound interest as if it were simple interest. So it makes it seem larger to you, because how much simple interest would you have to be paid to get the same as a lesser amount of compound interest? And often banks will give you APY, annual percentage yield, to inflate their figures. So if you see APY, it's giving you the interest rate in terms of simple interest that you would get for doing it in terms of a lesser amount of compound interest. Interesting way you can get played with numbers, or people will play with you with the numbers. APR is not the same as APY. It's the effective annual return. Let's look at another example. Marty invests $10,000 at 7.5% APR for 10 years. What will his final balance be if the interest is simple interest, compounded annually, compounded quarterly? Let's take a look. First of all, there's the information. Here's what we're given, and here's the final balance. We're going to look first of all at simple interest. If I put that up as a table, I see in terms of simple interest, when I work it out, I get $17,500, just following the formula. Compound interest compounded annually, where T is equal to 1 year. If I plug that in, since if I compound it once a year over 10 years, I'll be compounding it 10 times. Working that out, notice that 1.075 to the 10th power is 2.06. Then my final balance will be $20,600, more or less. Finally, let's look at the same problem, but this time compounded quarterly. T is equal to 1/4 of a year. There's the information, principal 10,000, the rate is 0.075, the number of compoundings. If we're going to do 10 years at 1/4 of a year, there would then be 40 times that we needed to compound it. There's the formula for compound interest for the final balance. Let's put the numbers in. We have the principal of $10,000 times 1 plus 7.5% expressed as a decimal times a quarter, that quantity raised to the 40th power. I know that sounds awesome. When we plug that in, a quarter of 0.075 is 0.019. Adding 1 to that, we get the expression 10,000 times the quantity 1.019 raised to the 40th power. I whip out my magic scientific calculator, rounded to the nearest 2 decimal places. That comes out to be 2.12. Doing the math, I get that B, the final balance, compounded quarterly, is $21,200. Now let's compare them all and see how we made out. Simple interest, final balance, $17,500. Compounded annually, simple interest, or final balance, sorry, is $20,600, and compounded quarterly, the final balance is $21,200. The reason these things go up is because you're using, or the money that you owe is being used against you either way more often, effectively once a year. With simple interest, you don't have to pay, or you don't get the interest. It's sort of like it's taken out. You don't have to worry about it. If it's compounded annually, it's added in once a year. If it's compounded quarterly, it's added in 4 times a year, and so forth. The more it's compounded, the more the interest either works for you or against you.